Okay, all set.
So maybe we can start.
Yes, please. Yes.
Okay, so I'm Laurent Rolou. I'm working in the Croco development team on the NBQ approach, led by Francis Auclair. We are working in a laboratoire neurology in Toulouse, in France. And my talk will present several applications of the Croco NBQ module that have been developed in our group in order to study the dynamics of the Strait of Gibraltar. Before to start, I would like to thank my co-authors from Laboratoire Neurology, as well as collaborators from CHOM and Lagos. Thanks, Patrick. I would like also to acknowledge our sponsors, namely the LEF program, Mercator Ocean International Company, for their financial support, the French Navy, CHOM, for the funding of 2 postdoctoral positions, the University of Toulouse for a PhD grant, and also the supercomputer facility here in Toulouse. So we'll talk about the Strait of Gibraltar. This is this narrow passage here that connects the Atlantic Ocean and the Mediterranean Sea. This is a unique entrance of the Mediterranean Sea, which is a semi-enclosed sea between Africa and Europe. The strait is bordered by Spain at the north, the territory, the English territory of Gibraltar here. And for the African part, you have Morocco and the exclave of Ceuta, which is a Spanish territory. The strait is of great importance for economic activities and for both continents, the world's busiest waterways. And it also features important defense activities. The strait is about 50 kilometers long and a width about 13 kilometers here at the narrowest point. The western end is about 40 kilometers, and we have something like 25 kilometers here at the eastern end. The depths range from 300 centimeters at cameronal seals or espartel seal here, and then something like 900 meters when you enter the Mediterranean Sea. So this narrow passage connects the Atlantic Ocean here, crossing the Gulf of Cadiz to the Mediterranean Sea, with marginal seas like the Alboran Sea and the Algerian Basin. From an oceanic circulation point of view, this is a place where there is an important amount of water exchange to balance the ocean atmosphere fluxes over the Mediterranean Sea. Because of the evaporation and the precipitation imbalance over the Mediterranean Sea, the Atlantic Ocean and the Mediterranean Sea have different salinity levels, and therefore the highly saline waters from the Mediterranean Sea flow outward and in depth. This is the Mediterranean jet here, whereas the less saline Atlantic waters flows inward and on top of the Mediterranean Sea current. You have another interesting feature here. There are the 2 anticyclonic gyres. Western Alboran gyre is some permanent gyre, and the eastern Alboran Gyre is more elusive. And these two features and their variability won't be discussed here in this talk. Please note that we have all these processes under the influence of large tides coming from the North Atlantic. So we'll focus on small scales processes that are occurring within the strait with typical length scales less than 1 kilometer. The ocean circulation within the strait is a two-way exchange, we have seen, directly influenced by the interaction between the intense tidal forcing coming from the Atlantic Ocean and in a complex bathymetry. As you can see here, the bathymetry again with seals and deeper channels. Several processes contribute to the mixing of the water in the strait. You have first small amplitude internal waves here at the interface of Atlantic and Mediterranean waters. You have already seen the hydraulic control in the previous presentation by Patrick here over Camarine seal, and consequently an hydraulic jump. Here in C you have shear instabilities provoked by the control, and when the hydraulic jump is released, you have this internal solitary waves propagating as a train. So we'll discuss about all that in this presentation. Here we see the surface signature of these internal solitary waves as they can be seen by from space by ERS-1 synthetic aperture radar instruments from pioneering works 1996, I'm sorry for the mistake, or recently by Sentinel-1B SAR instrument. They can be also observed by hyperspectral imagery like MODIS, onboard Terra mission, or ocean and land color imager. You have surface signature here, or this multispectral instrument on board Sentinel-2 mission. You have here surface signature. You can see this surface signature also by optical imagery. It can be seen from the International Space Station here, or from Pleiad high-resolution imager. You have lots of details on that picture. The hydraulic jump surface signature can also be observed by Pleiad mission. Here you have the surface signature of the several points of control over Camarine seal, or even be with a personal camera, like during the Gibraltar 2002 campaign here by Frank Dumas. So to study the flow dynamics in the strait in further detail, in particular in the interior ocean, realistic numerical modeling is of great help. And early attempt used two-layer model for the exchange flow. The increase of computational power led to 3D modeling in early 2000 years. And we increase of vertical resolution and horizontal resolution as well, explicitly addressing the tidal cycle and the flow characteristics. But some aspects of the dynamics could not be well reproduced by hydrostatic numerical model. We have seen that previously with Patrick's presentation. So in particular, the evolution of the internal tidal bore generated at the main seal, at camerinal seal, cannot be well reproduced. So this wave is strongly nonlinear and strongly non-hydrostatic, and it cannot be reproduced by hydrodynamic model. So recently, more realistic non-hydrostatic model like MIT GCM have been used to represent explicitly the internal solitary wave. And recently, we complement here the list with a Croco model, state-of-the-art NBQ module, recently presented by Patrick, and with some literature here from Hilt et al., Marchesiello, and more coming. We have seen already lots of this its features, but basically there is a non-hydrostatic approach based on the relaxation of the Boussinesq approximation in the fast mode solver, donc resolving all waves down to acoustic waves. It can be used for LES or DNS problems. It features monotonicity preserving schemes. It's really important, like WinO5 TVD, and fully turbulent 3D closure schemes. And this Croco model comes also with a grid refinement capability with Agrif library. So it's a perfect candidate for us for use in the modeling of the dynamics in the Strait of Gibraltar. So after this brief introduction to the Strait dynamics, I will review some interesting features of the NBQ module, which are available in the Croco code. And first, I will show a 2D vertical slice model option, which can be nice for investigating some NH details like resolution or advection, SGS models, and so on. Then we'll go to a fully 3D model option for LES and the route to the turbulence. And finally, we'll see the mesh refinement capability brought by the Agrif library, and for the interactions of the scales studies. So first feature is a 2D vertical model of the strait, just to investigate details of the dynamics. It's quite simple and so relatively computationally efficient, and it incorporates the configuration of seal characteristics in the region. So you have the bathymetry here, you have the transect from the Gibraltar experiment led by Farmer and Army in 1988, which help us to define the horizontal grid and the X direction. On the vertical, we have 40 sigma levels and we choose a 50-meter discretization. So we are a number of points along X, Y, and Z. To have some reality, we use a 100-meter resolution from Miscara et al. So to do this, this S2DV grid, so vertical slice, plus realistic bathymetry, we adjust some Croco tools routine and create the make batygrid.m routine. Another point is the stratification. We start the model with a lock exchange configuration adapted from the work by Sanino et al. It is well adapted for starting this kind of model. We use the T and S profiles from Braden et al. And the forcing of tides is directly adjusted in CLM tide F routine from values extracted from the TPXO8 atlas. For this experiment, no atmospheric forcing is used. And after a 3-day spin-up, after the lock exchange, we run a 5-day 10 M2 period run with the time step for the slow mode is 1 second, and it is a 1/8 second time step for the fast mode. I will show here the main CPP key for this S2DV model. Of course, the NBQ key. There is no need to run the code with the key NBQ precise. Just NBQ perf CPP key is enough. Of course, the S2DV for the 2D vertical grid, but no change for the rest, new sigma coordinate chord, and also the masking CPP key to take into account the bathymetry. We have a tidal forcing imposed by the tides and CPP key, sorry, and so OBC NBQ Orlansky for the boundary condition, and north-south periodic CPP key as you need to maintain the flow in the vertical space. In the advection scheme section, I will advocate, as Patrick mentioned just before, for dedicated advection schemes such as TVD or Win5 if you use a subgrid scale closer, such as GLS or Smagorinsky, just to avoid the numerical diffusion in your simulation. So this is already shown by Patrick, but it is really important to get rid of this noise. In this first result, we compare two simulations on same vertical 2D vertical plane. Here you have a classical hydrostatic simulation with a horizontal resolution of 200 meters, 220 meters, sorry. This is more or less the resolution of the best OGCM model in the region. there is 40 sigma levels on the vertical. And here you have a non-hydrostatic NBQ simulation like previously described. The contour plot are vertical velocity. In blue-red, blue is negative and red is positive, with isopycnal surfaces overlaid. So when you look at the NH simulation on this panel, you can see explicit primary shear instabilities, like that, that have been identified as Kelvin-Helmholtz type instabilities, developing at the interface of Atlantic and Mediterranean water. Of course, you don't see that kind of small scales processes in that hydrostatic and lower resolution simulation. But this is not a story of non-hydrostatic physics or high enough resolution. If we show the same kind of contour of vorticity this time along the y-axis in grayscale, still with isopycnal surfaces, and at the beginning of the outflow. If we compare two non-hydrostatic simulation, this one is at 220 meters, this one, the B1, at 50 meter resolution. You can see that even if you have a non-hydrostatic physics, you do not resolve the shear instabilities here. And if you look at this one, this is hydrostatic simulation of 50 meter resolution. Even if you have 50 meters resolution, you don't have the onset of the turbulence and the primary instabilities, because you have the hydrostatic physics. So my message here is to you is that you need both NH physics and high enough resolution to go to the way to turbulence in the ocean. You cannot separate one of them. If we have a look now to internal solitary waves, I can show you here. You have the velocity field here on grayscale. This is a W. This white line is a specific isopycnal surface. You can see here, after the release of the hydraulic jump, the starting of waves and propagation as a train of solitons. The amplitude of the first wave reaches 100 meters at this 200 meter depth. The solitone train amplitude increases and exceeds 150 meters as it propagates over the flop in the Tarifa arrow here. Then the wave amplitude decreases and it propagates in a region where bathymetry is deeper. In this part, we will represent the depth evolution of this isopycnal surface as a space and time diagram evolution. Regions of sharp or horizontal density gradients can be notified periodically, like in the region of camarine seal. They correspond to the generation of hydraulic jumps. And the propagation of internal waves are identified by the tilt of isolines whose slopes provide an estimate of wave propagation speed. So you have the first mode here with 1.5 meter per second, and this one generated a bit before camarine seal, with which is in mode 2 internal solitary waves with a speed of 0.9 meter per second. Here we present on this part, on the left part, the density anomaly fields in the region of the Tarifa narrow, somewhere like here, at the end of the simulation. On the top panel, you have the hydrostatic simulation. And here you have a result from the NH simulation. We can see that mode 1 and mode 2 large amplitude internal waves are generated at the camarine seal, both simulation, and propagate eastward during each ebb in both simulation. However, a wave train can be only identified in the non-hydrostatic simulation. The hydrostatic case is, in this case, the non-hydrostatic dispersion is missing and produce internal waves that are propagating only as internal bores. In the non-hydrostatic case, the internal waves can propagate as train of solitons with a varying number of solitons and speed. On this picture, we illustrate the train propagation in the S2DV simulation in a comparison with a SAR observation. So we compute a free surface slope of the S2DV simulation, and we can see that the train of solution is somehow comparable with the observation. So to summarize, we have a nice and efficient way to make primary investigation here on the small scale feature of the Strait of Gibraltar. This S2DV is really computationally efficient, but you need to include both NBQ physics and high resolution, horizontal resolution to have the good level of realism. The characteristic of the simulated internal waves compare qualitatively well with published observation and also with numerical studies. Despite some shortcomings of this 2D representation, like simplified bathymetry, like the impossibility of the generation of secondary instabilities or any transverse and reflection along the north-south direction, for sure. So, based on this previous work, we can go to a full 3D model of the strait and to take the advantage of all the things that have been explored. So we maintain a horizontal resolution of 50 meters, 40 sigma levels on the vertical. We use the same high resolution bathymetry, which is now a full 2D map. The lateral and initial conditions are provided by the Mediterranean Sea system of ENEA organization. They provide tidal forcing as well with 4 major constituents, namely M2, S2, K1, and O1. We still not applied no atmospheric forcing or fluxes in this simulation. And note that we have adapted some MATLAB routine to take into account the large grid we have now with this 3D full model. And also to take into account interpolation and masking issues between the forcing OGCM and the high resolution grid we have. So we run a 2-day spin-up with the hydrodynamic version of Croco. And then we run a 4-day simulation with the full NBQ model. Here are the keys, the CPP keys. So still NBQ, NBQ perf, CPP key. The schemes, the advection schemes, you can use Win5 if you use GLS, for instance. And now we have a tidal forcing. Sorry, this is a typo. You don't have to define this NS periodic. Now you have a full tidal forcing in this 3D configuration. So here we show an animation of the Z-axis vorticity field of the surface current. You can see many small-scale features in this animation. To start with hydraulic controls here at the camarinal seals, that you have many points of controls in this area. You can see the formation here of the jump. It's relaxation. Solitary waves are propagating eastwards. You can see in this region reflections at the coast. And note that you have trains of solitons with more than 3, 4, depending on the tidal cycle. And you can focus here now to see the interaction of a mesoscale AD, which is formatted now by the first passage. And then you have an interaction with internal waves and deformating the bore. And after that, you have the vanishing of the train when you enter the Alboran Sea. So we can see that all features are present in our simulation. Hydraulic control, the relaxation of the hydraulic jumps, internal solitary wave generation, propagation, and reflection, and with trains of solitons. You have already seen this animation just previously in the talk of Patrick Marchesello. This is the contour of vorticity in the full 3D now model. You have the direction of the flow, contour of vorticity in color, and isopycnal surfaces here in black lines, in solid lines. So you can see the evolution of the hydraulic control here over each tidal cycle, and generating then relaxing an internal hydraulic jump, mixing by shear instabilities can be seen along this slope. This is Camarine Alcine. So you have the development of the instability, the jump is forming. And when the jump is active, you have the propagation of the train of solitons towards the Mediterranean Sea. What can be interesting in this map is this is the surface anomaly, and this is a transect of this picture here. You have the tidal cycle, and you can see what can be called boiling waters by the fishermen. From here, they experiment this kind of boiling waters in the ocean, and this is the surface signature of all these intense activities. You have the formation of the control here, approaching the lower tide. Several points of control. So this is connected with the jump. And you have the boiling water there. So we can have a nice feature here. You can see shear instabilities, propagation of the internal waves, and this simulation allows the investigation of shear instabilities in the density flow west of the Camarine Alcine. Here with the same transect, we have a view starting from here. North is there, west is there. This is an interesting diagnostic proposed by Margot Hilt during her PhD thesis. This is to use the Q parameter, which is the second invariant of the velocity gradient tensor. It's kind of a 3D generalization of the Okubo-Weiss parameter. which measure the importance of deformation versus rotation. So when Q is strictly positive, rotation is larger than shear. And here we present an animation of the evolution of the parameter in this region. In the Mediterranean water vein, actually, for a value of 10 minus 4. The Q parameter is in red, and this is a surface constant salinity surface. Here, 38.5 PSU. So this is the temporal evolution of this parameter. You can see the limitation of a 2D vertical representation because you have the extension of this billows along the cross-shore strait. The temporal evolution shows the oscillation here of the Q parameter between high positive values at the center of the billow and low negative values is between two consecutive billows. Show it again here. This transect, you have the instability, and you can see the roll-up of salinity here, carried westward and out of the Mediterranean Sea by the Mediterranean waters. So a few examples here of the 3D model using the NBQ Croco model. Nice results on the internal solitary wave propagation generation, and also an interesting characterization of primary shear instabilities at Camarine Seal. This study stresses the need for a new diagnosis because we are entering LES simulation, and Margot Hilt proposed the Q parameter for the detection of shear instabilities, and she also developed some interesting diagnostics. This is background potential energy. I do not show it in this presentation, but this is a new metric for the diapicnal mixing evaluation. So these metrics are essential to evaluate these LES models, and then go towards a better representation of the diapicnal mixing in the ocean and in climate models as well. In this final part of my talk, we'll see another development in the NBQ module, which is the grid refinement capability using Agrif library, which is already used in the Croco hydrodynamic section. Briefly, for this development, we have introduced the two-way exchange in the fast mode for the NBQ variable. And we have tested it on the classical vortex implementation test. This is a test case released in the cppdef.h file when you want to test a grid refinement. So this is an idealized experiment where you have a grid refinement here, the parent grid at lower resolution, and you have a baroclinic vortex propagating on a beta plane. So now you will see that you have the continuity of the zeta fields between the high resolution model and the lower resolution model. So to do this, you have to define vortex, test case, NBQ, of course, and define Agrif and Agrif two-way for the two-way exchange. We have tested also in a one-way nesting configuration. So after validation of this development with this test case, we go to this refinement strategy, starting from this domain, which is called BR4. This is starting from Portugal here to the exclave of Melilla. The domain is the grid is a 900 meter grid, where we have an embedded grid, which is named HF4 here, with a ratio factor of 5. So this grid is 180 meters. This is comparable of some previous resolution we have previous slide. And in this HF4 grid, we have an embedded VHF4 grid at 60 meter resolution over the Camarines seal to track the instabilities. So this is a large grid with more or less 600 points in X, 300 on the Y, and 40 sigma level on the vertical. And the CFL condition imposes some time step, about 15 seconds for the parent grid, 3 seconds in the strait, and 1 second over the Camarines seal. So the idea is to have the full domain with tides entering the inflowing of the Atlantic waters and the outflowing of Mediterranean vein, and to see interaction with the small case in the strait. To do so, we use the Nest GUI graphical interface provided with the Croco tools. We use the same input fields for all grids, which is simpler for continuity. So we use the same bathymetry as before, 100 meter resolution. Tides are provided by the TPXO9 atlas, and we use a full 10 constituent spectrum. Initial and lateral conditions are interpolated from Copernicus Marine Service. We can use both forecast and analysis. And bulk and surface fluxes this time are included in our simulation, and they are interpolated from the global forecast system, the GFS. The resolution is 1/4 degree, and we use only forecast. And finally, Lancy mask is built from the shoreline dataset from NOAA, from Wessel and Smith. To build this Lancy mask, we use the Fortran code by Alexander Shepetkin, and then we edit the mask with the edit mask interface from the Croco tools. And to do all these things, in particular for reading the CMEMS and the TPXO9 fields, we have made some minor modification to Croco tools. So in the framework of the Jupyter project, in which we are in charge of forecasting the ocean for a campaign, an ocean campaign. We have developed this configuration, and we are testing different configuration. The first one has no nesting. We use the full BR4 domain in NBQ using the NBQ module. With one child grid, we apply a two-way change over this HR4 grid here. This is the RIA2 experiment. And we perform a double nesting, as mentioned. The first one is in this region, then over the Camarine seal using this VHR4 grid. And this is the RIA3 experiment. And we are conducting preliminary investigation on the sea level as tides are the first order forcing of large internal solitary waves. And we'll have a look on the surface current divergence, which can be seen as a proxy of, this is a surface signature of internal solitary waves, and it's comparable to SAR images. First of all, we present sea level comparison during the campaign, during the JPEG2 campaign on the 19th of October. We compare sea level from here, the BR4 model, and on the right, the RIA2 model. With respect to observation acquired in real time during the campaign and provided by the European Research Center and Puerto del Estado for Tarifa, GRC is providing Portuguese stations. The comparison are presented from Atlantic to the Med. Actually, Tarifa is in the Strait, not totally the Med. Model sea level is in blue, observation are in green. And for Sagres and Albufera, we can see that the grid nesting has reduced the time lag between observation and simulation. For these two stations, we have a positive impact on time of the phase of tides, but we have a decrease of the amplitude of the signal. However, the two elements combine in a reduction of 10 to 15 centimeters of the root mean square error from 45 centimeters here down to more or less 30 centimeters in the RIA2 simulation. This RMS error reduction is mainly driven by the time lag reduction. In Tarifa, there is no loss of variability in the sea level signal, and the time lag with respect to the observation increases. So we have good performances away from the strait and negative performances in the strait in Tarifa. If we compare RIA2 and RIA3, that is to say, when we add an embedded child grid over the cameral seal here, we have an increase of sea level variability for Sagres and Albufera. So you can see we have now more or less the same amplitude of sea level signal in the observation and in the model. This leads to a diminution of root mean square error from 30 centimeters here down to 15 centimeters there. There is no significant change for the sea level in Tarifa. So maybe the gain of energy is the expected sign of a better transfer of energy between the different scales, and with the internal mode good representation, now we have the instabilities in the shear instabilities over cameral seal. This has to be confirmed with in-depth comparison of vertical profiles, for instance. These figures illustrate now the surface signature of internal solitary waves and the hydraulic jump here and there as a proxy of surface rugosity retrieved from the synthetic aperture radar observation. We are still on the same date, the 19th of October, and we are illustrating these divergences of surface current at the intermediate high resolution grid. If we compare both systems, RIA2 and RIA3, this is one child, two child system, we can see we have more fine scale dynamics over the generation area here and there at cameral seal, and with more intensity in this RIA3 simulation than in this RIA2 simulation. And we can see minor differences as well in between the two models on the patterns here and there of the internal solitary waves, maybe due to an advance in wave propagation in this RIA3 model. We represent now the same divergence field computed for the BR4 model and still the RIA3 model, both figures represent as the fields at the lowest resolution. This is the resolution even in the RIA3, but at the 900 resolution parent grid. The difference between these two figures, this is the parent grid, and this is the field at the parent grid resolution after upscaling of the two embedded child grids. This is a major difference. We can see the impact now of the grid refinement, which allow downscaling to have the primary instabilities and the upscaling of all this energy. We observe more fine scales and more energetic, even it's the same resolution. We have more energy over the strait. And we can see also a significant pattern between the wave propagation at the eastern end. Here you can see this kind of pattern, and now we have a pattern which is more in agreement with what has been done in the 3D model, and also what we can observe by satellite. So this all this will have to be confirmed with the Proteus GP2 campaigns observation, and we'll also have to compare with some satellites observing at these times. So I come to my conclusion, and I hope I have convinced you that the Croco NH module is ready for realistic run. Even in real time, we have experienced this nested configuration for forecasting systems. It works. So we have enhanced physics for LES and DNS problems, and also a nesting capability now in the NBQ module for studying scaling interactions. Of course, we still need observation to validate all the findings we have, and this is the object of two field campaigns. When was in September 2002, and the next one in September 2002. Previous one when 2020. Our investigation continues over the straits, in particular on large-scale upscaling of this small-scale dynamics, in studying the diapinal mixing properties and evolution, and in adding interaction with the atmosphere, with a coupling with a Meteo model. And from a development point of view, the future evolutions will concern the surface and the interior ocean couplings, hydrodynamic and non-hydrodynamic evolution of these several fields. We'll work on the bottom interface condition for acoustic gravity waves, and we'll have some job in progress to improve the efficiency, the computational efficiency of the code with both physical and computational efforts. So that's it for me. Thank you very much. And if you have questions.
Thank you, Laurent. Very impressive, realistic configuration, no?
Yes. It's not a job started yesterday, so we have we have a long way, but I think this kind of studies can be reproducible somewhere else.
Well, I was when you spoke about this boiling water, I've seen some of that in the Chacao channel here in Chile. We have a highly energetic tidal channel with currents about 3-4 meters per second, and I've seen this surface expression of the boiling water is impressive.
Yes.
Maybe if I get some good bathymetry for the area, it will be.
The bathymetry is important. Yes.
Yeah. Well, so the way the tides on the boundaries, you include them from the tidal forcing in that case?
In that case, we use TPXO9. It's multi-resolution, but for main constituents, it's about 1/30 degree. So it's you have good resolution, and this is a product with data assimilation. So it's really precise. For the moment, we don't have analyzed what is our tide computation. So we have a good forcing, but we don't have enough simulation time to perform a tidal analysis. So for this double embedded imbrication embedded model, we don't have. We have 10 days. That's not enough.
Okay. So there are some questions about the size of the files of this simulation. Well, this is we can see here the how
yes.
often are you saving these results?
Size matters in this case. For the forcings, it's not so much. You have nice strategies. You can use climatologies or boundary forcing fields option. We use both of them. And resulting fields depends of how much you need in time resolution of the archive, in the number of variables. It can be big.
Okay. There's another question about the difference between the two sea level anomaly slides 29 and 30.
In this one, you don't have nesting. This is the model at low resolution. No Agrif zoom. You have one Agrif zoom here. And in this one, this is the same, one Agrif embedding grid and two embedded grids.
Okay. Yeah, that's fine. Thank you.
So the first one, sea level over there in so I can show that Sagres is here, Albufera is there, and Tarifa is there. And we don't have not so much tide gauges in these regions. So sea level is pretty good here with this BR4, not when you add one zoom, but is already good and even better when you have this third grid.
Okay. Thank you.
There's one more question, Joseph. I don't know if you want to explain it.
Yes. I was wondering whether you could use this, for instance, if you wanted to study out there, something out there in the ocean, and as they propagate closer to the shore, you want to capture some of the nice features. Could you use this multi-grade approach to do that, so that you have, let's say, a hydrostatic setup, away from shore, and then as you get closer, you can use the non-hydrostatic capabilities to capture what is happening there?
Yes, the point is, it's a good idea. There is no need to run the non-hydrostatic stuff here. The point is that the Agrif library uses the same CPP keys over the 3 grids. So we impose non-hydrostatic here and there. So we have the NBQ module over the BR4 domain. Actually, this is not so much. The cost is not so much, because when you run this domain once, this one is running 5th time, and this one 3rd. So you have 15 run of that for one of NBQ simulation over the BR4. So the cost is not so much. The overhead is not so much in this case.
Okay.
We have developments that will separate some propagation. We actually, for tides, we don't need the non-hydrostatic surface elevation. So we have development to. This is in my perspective slide. We will separate physics and propagation to accelerate the computational cost.
Okay, thank you.
You're welcome.
Any more questions? Well, if not, thank you, Laurent. I will stop the